Welcome to the fourth video of the FP3 chapter, Hyperbolic Functions. To start us off in this video, a little challenge for you to write down as many P3 trigonometric identities as you can remember. Pause the video, give it a go. I'm not going to write them down on the screen. This is just for you to practice some active recall of those identities. And there is a reason for this. So give that a go. Hopefully you've paused it and tried it and had a few identities written down. In this video, we're going to make use of some of those identities, probably at least one that you've written down if you did that. And we're going to prove a couple of identities. So we're going to look at what they are, a couple of examples specifically, not all of them, obviously. More to the point, we're going to look at how to arrive at them using something called Osborne's rule. And then the only video left in this chapter is to apply what we've learned so far to solve equations. So let's look at a few hyperbolic identities. And in some ways this is nice and easy, because a lot of the trigonometric identities have got corresponding hyperbolic identities. But there is, as I've said here, an important caveat. There is an important warning. You need to be careful to apply Osborne's rule correctly. And I'll give an example first, and then we'll look at what that rule is. So the example I've chosen, which I'm sure if you wrote down any identities, you included this one, cos squared x plus sine squared x is exactly identical to 1. Remember, this 3-line equals means any value of x can go in here and it will still be true. So there is a corresponding identity in the hyperbolics, but it's not quite the same. So if we look at this and we give it a try, using the definitions, we can square this, add them together, and hopefully you can see that this middle term here, 2e to the x e to the minus x, and over here the minus 2e to the x e to the minus x are going to cancel out, and we're going to double up on the first and the third terms, which is going to give us this, which, although it might be useful in some very specific circumstances, is not very useful in general circumstances. But if we get rid of all of that and we change our identity ever so slightly, and we try cos squared x minus, not plus, minus sinh squared x, and give this a go, we find when we get to this point that our first terms cancel, our third terms cancel, and the middle term doubles up. Minus 2 becomes a 4, e to the x e to the minus x over 4. And of course e to the x e to the minus x cancels to give me 1, and the 4 and the 4 cancel as well, so that is equal to 1, regardless of what x might be. So here is the corresponding hyperbolic identity for this trigonometric identity. And this is a nice example of Osborne's rule, which we'll look at now. Osborne's rule says you can change any trigonometric identity into its corresponding hyperbolic identity if you follow these 3 simple rules. First, very obvious, change your sin x's into sinh x's. Second, just as obvious, change your cos x's into cos x's. But the third one, the important one, that does occasionally trip people up, is to replace any product of 2 sin x terms with minus the product of 2 sinh x terms. And that's why on the previous identity we ended up with a minus sinh squared x. So this bit here is the important part to remember, and is the easy part to forget. So what this means, sin x's become sinh x's, that's fine. Cos becomes cosh, that's fine. And if you put these two together, you find that tan will always become tanch. That's great. And of course, if you do 1 divided by sine, that becomes 1 divided by sinch. So we can see that the reciprocals, the cosec and sech and coth, will all come from cosec, sec, and cot, respectively. We can also see that if you replace your cos with a cosh, and you do that twice, then you're going to be replacing cos squared with cosh squared. But with the sine squared, this is where the third rule comes into play. When you've got a product of two sine x terms, it must be replaced with the negative product of the two sinh x terms. Even easier to forget is that it's not just sine x terms multiplied together, it's if there's an implied sine x term multiplied by a sine x term, which means tan squared, because if you just expand that out, tan squared is sine squared divided by cos squared, the sine squared becomes a minus sinh squared, and the cos squared becomes a cosh squared, so your tan squared, when you change from a trig identity to a hyperbolic identity, becomes a minus tanch squared. So even if it's not explicit, if it's hidden within other terms, any sine squared, any product of two sine x terms or implied product of two sine x terms must be replaced with a minus product of two sinh x terms. So I hope writing all of those 6 down makes that a little bit clearer. So I should have clicked on that sooner. We've already explained why that is, because it's an implied product of two sine x terms. Okay, so let's work through some examples, because that's the rule, and it means that any trigonometric identity can be turned into a hyperbolic identity, but you've got to apply the rule correctly. So I'm going to go through a few of these examples. We've got 4 examples. Write down an identity for sinh a plus b using Osborne's rule. So using Osborne's rule, that means I need to start with a trigonometric identity, otherwise I've got nothing to apply the rule to. And I know that my sin a plus b is equal to sin a cos b plus sin b cos a. Now I'm pretty sure that one is given in the formula booklet. So that, using Osborne's rule, gives me a hyperbolic identity sin a plus b equals sin a, oh, I messed it up, sin a cosh b plus sin b cosh a. Always double check that you have not got a product or implied product of two sine terms. So here we've got a sine times a cos and a sine times a cos, so that's fine. There's no sine times sine, so I didn't need to replace anything with a negative. So this just transforms directly. But question 2 is a little harder. Prove this is true using the definition of sinh x. And this is actually quite a challenging question if you do what would normally happen is start with the left and make it look like the right. So what I'm actually going to do is use the definition of sinh x and the definition of cosh x, and I'm going to start with the right hand side, the more complicated one, put all the definitions in and show that it simplifies and can then be replaced with the left hand side. And generally speaking, I would suggest this is probably the way to approach proof of an identity like this. Start with the more complicated side, put the definitions in, and expect it to simplify. Because if you start with the simpler side, put the definitions in, you're not always going to be sure how to manipulate it to get what you need, to get the more complicated side. I hope that makes sense. Okay, so I'm going to give this a go. I might make a few mistakes, but hopefully not too many. So I'm going to start with the right hand side. So sinh A cosh B. Now I don't have too much room, so I'm going to start with the definitions straight away. So that would be e to the A minus e to the minus A over 2 times cosh B, which is e to the B, plus e to the minus B divided by 2. That's going to be really annoying if that keeps happening. So we've got e to the A minus e to the minus A over 2 times e to the B plus e to the minus B over 2 plus e to the B minus e to the minus B over 2 times e to the A plus e to the minus A divided by 2. So putting all of those definitions into sinh A cosh B plus sinh B cosh A. And the question is, can I manipulate all of this and simplify it down to prove that it is indeed sinh A plus B? And that's just going through the algebra. So this thing, the first term, if we multiply all of that out, we get e to the A e to the B minus e to the minus A e to the B minus e to the minus A e to the minus B, and then we finally get plus e to the A e to the minus B. And you can see we've got all the different combinations there. And we're going to have plus, and then the second term, we're going to have e to the B, e to the A, minus e to the minus B, e to the A, minus e to the minus B, e to the minus A, plus e to the B, e to the minus A. And all of that is making one big fraction because they've both got the same denominator, 2 times 2, which is 4. Okay, it looks horrible, but a quick scan tells you that we can simplify some of these because we've got some terms coming up that are the same. So we've got e to the A, e to the B, which is the same as e to the B, e to the A. We've also got minus e to the minus A, e to the B, which cancels with e to the B, e to the minus A, because that's a positive. We've got minus e to the minus A, e to the minus B, minus e to the minus B, e to the minus A. So they combine. And finally, e to the A, e to the minus B, minus e to the minus B, e to the A. So they cancel. So we can simplify this quite a lot to become, we've got in green here, 2 e to the A, e to the B, and the white ones minus 2 e to the minus A, e to the minus B, all divided by 4. Now, of course, I can also cancel my 2's with the 4, and using rules of indices, I can combine e to the A, e to the B as e to the A plus B, minus e to the minus A plus minus B, or minus bracket A plus B, divided by 2. And that is equal to the definition of sinh with the bracket, where of course my bracket here is A plus B. which is my left-hand side of the identity. And I hope that also makes it clear as to why working with the left-hand side and trying to make it look like the right-hand side will be a bit of a nightmare, because going this way, yes, okay, you could put that in very easily, but the change from here to here, you wouldn't necessarily think to multiply everything by 2, and you certainly wouldn't necessarily think to start including these terms here, which have all cancelled nicely going the other direction. So starting with the more complicated side has helped us here. And we have proven that sinh A plus B is indeed equal to sinh A cosh B plus sinh B cosh A, which is very similar to the trigonometric identity. Number 3, fairly straightforward. Write down, not work out or prove, write down the hyperbolic identity corresponding to these two identities. So the only thing we need to be wary of is that third part of Osborne's rule, which is the product or implied product of two sine x terms. So in cos 2a, I don't have any sines coming in. So we've got cosh 2a must be identical to 2 cosh squared a minus 1. No sines to worry about. And the second one, tanh a minus b must be equal to tanh a minus tanh b. Now they've both got a sign inside them, but they don't have a sign multiplied by a sign inside them. So I'm okay. And 1, but on the bottom here, tanh a multiplied by tanh b, if you put that in terms of sinh and cosh, you would have a sinh a times a sinh b on the bottom there. So I need to replace that with the negative. So that, again, that's that third part of Osborne's rule coming into play there, because of an implied product in these two tanh terms. When you multiply the two tanh terms together, there's a multiplication of two sinh terms going on inside there. So this is the tanh a minus b, slightly different to the tan a minus b. And question 4, given that sinh x is equal to 3 over 4, find the exact value of cosh x, tanh x, and sinh 2x. Okay, so obviously if you had a calculator and it was able to do this and give you an exact answer, that would be one way. But we're trying to use the hyperbolic functions here in terms of the hyperbolic identities, so I'm going to use identities to do all of these. So if we know what sinh x is and we want cosh x, probably the easiest one to use is going to be cosh squared x minus sinh squared x is equal to 1. And you can see now why this is true, because if you do cos squared x minus cos squared x plus sin squared x is equal to 1. If you start with that trig identity and apply Osborne's rule, the sin squared x needs to change into a minus sin squared x. So in terms of Osborne's rule, that's why there's the minus there. So if I use this, I can see that cosh x is going to be equal to the square root of 1 plus sin squared x, which is equal to the square root of 1 plus 3 over 4 squared, 9 over 16. 1 plus 9 over 16, we get 25 over 16. Square root of that, 5 over 4. If you think about your graph, cosh x in terms of the range cannot be less than 1. So 5 over 4 must be the answer, not negative 5 over 4, despite being a square root, because of the definition of cosh x, the limit on what that can be. Okay, the tanh x is fairly straightforward, because tanh x is the same as sin x divided by cosh x. And we know sin x is 3 over 4. and cosh x we now know is 5 over 4. So we can cancel those to give us 3 over 5. Finally, sin 2x, again we're going to use an identity here. The identity we're going to use is sin 2x equals 2 sin x cos x. We're going to change that using Osborne's rule into sin 2x is equal to 2 sin x cos x, and I don't have two sines multiplied together, so I don't need to change anything into a negative. And in this case, I know sin x is, that's very annoying. I know sin x is 3 out of 4, and cosh x, if I remember, was 5 out of 4. Which gives us, that can cancel with that, gives us 15 over 8. And that is the end of the examples. A quick note on what's in the formula booklet. There are only these three given to you. But everything we've just said about Osborne's rule means that as long as you're careful, you can manipulate and transform all of the trigonometric identities in the P3 section as well. So a quick scan down the list. This one is okay. This one has got a sine times a sine, so your negative positive would change into a positive negative when you change these into a hyperbolic identity. We've already talked about this one, that will change. This one's okay, this one's okay, this one's okay, and this one, because you've got sine times a sine, that negative, there'll be another negative come in, so that will become a positive. So you've got to be a little bit careful, but there are more hyperbolic identities that you can write down using Osborne's rule based on these trig identities. And if you've got your textbook there, you can now practice questions 1 to 4 from exercise 1D. Only 1 to 4 because questions 5 onwards are to do with solving hyperbolic equations, which we'll talk about in the next video. Apologies for the technical problems.